Hello viewers, welcome to today's lecture on the instruction set, the vocabulary of the machine. If you want to interact with somebody or want to develop friendship with somebody, then the best way to do it is to learn the language of the person speaks. Obviously, in this course, we are interested in having close interaction with microprocessors and microcontrollers. So, you have to learn the language of the microprocessor and microcontrollers. The language the microprocessors and microcontrollers understand is known as machine language. And the machine language for different microprocessors may be little different. But in machine language, each word is known as instruction. So, each word in machine language is known as instruction, and the set of instructions which a microprocessor understands is known as the instruction set, which is the vocabulary of that microprocessor. That vocabulary will be different, little different from one processor to another processor, but very similar. If you look at the human languages, you will find that there is wide diversity. If you know one language, then it may not be necessary that you will understand the language of another person speaks. For example, in India, you have 18 different official languages, and each language has its own dialects with some variations. And even in India, language people speak in one region may be very different from the language that is spoken in another part of the country. But fortunately, the situation is not so difficult in the case of machine language. The reason for that is the different microprocessors are realized are based on the same underlying principle. We have already discussed the von Neumann architecture. All the microprocessors and microcontrollers are based on von Neumann architecture. Moreover, they are realized with the help of the same technology, that is your VLSI technology. As a consequence, the instruction set is not very different, and if you understand the instruction set of one microprocessor, it will not be very difficult to understand the instruction set of another microprocessor. So, that is one advantage in case of machine language. Now, as we know, inside the machine, the world is binary in nature. Everything is represented in terms of zeros and ones. So, an instruction will be nothing but a sequence of zeros and ones. For example, here I have written a small program which comprises a set of instructions, and it is stored in main memory. Main memory of the microprocessor system or microcomputer. Now, as you know, the memory is organized in terms of bytes. A byte is comprises of 8 bits, and the memory locations are organized, addressed in terms of bytes. For example, this is one memory location, this is another memory location, this is another memory location, and each memory location stores 8 bits. So, the instructions are stored one after the other in memory locations, and the instructions, the way it is stored here is machine language. Machine language. As you can see from this sequence of zeros and ones, a human being cannot make out what this bit sequence represents, what this bit sequence represents. So, for human interaction, For better human interaction, some steps are taken. One simple step towards this direction is to represent these instructions in terms of hex numbers. For example, this is your 3A 0011 1010 0011. These 4 bits in hex form is 3 and 1010 is A. So, this is the hex representation of this bit sequence, this byte. So, each 4 bit gives a hex number 3 and A. Similarly, the other bytes can be also written in hex. So, 3A 00, this is 47, this is 3A, this is 3B, this is 00, this is 80, this is 32, this is 00, this is 32, this is 3C, this is 00, and this is 76. Even this hex representation is not good enough, although it is represented in terms of some characters which human beings are familiar with, still the human being cannot really follow what they really mean. So, for better human interaction, these instructions are represented in a little different way with the help of mnemonics. In which each instruction is represented with the help of a with the help of a symbol. That symbolic name signifies or specifies what operation it performs. In other words, that mnemonics is representative or descriptive of the operation a particular instruction performs. For example, these 3 bytes 3A, 3A and 00, these 3 bytes represent an instruction LDA 003A, and this is address. What it does? Load accumulator, the mnemonic LDA stands for load accumulator, and 003A is the memory location. That means with the help of this instruction, the content of the memory location 003A is loaded in the accumulator. So, this is the operation, this is the instruction 3A 3A00, or these 3 bytes up to this represents this instruction. Then 47 or 0100 or 0111 represents the instruction move BA. What it does? It from this mnemonic representation or symbolic representation, we find that we can understand very easily what it really performs. It moves the data stored in accumulator to another register B. You know, inside the microprocessor there is a register, general purpose register B, so that data from the accumulator is transferred to the accumulator B. That is the operation performed by this particular instruction, and this instruction is only 1 byte in length. The next instruction again performs load operation LDA 003B hex, and the instruction is of 3 bytes in length. Similarly, 80 performs addition operation. This is the mnemonic for this instruction 80, which is in hex, add B. So, it performs addition of the content of the accumulator with that of the register B. Then next instruction stores the result STA in location 003C, and the instruction goes up to this. So, it is also a 3 byte, it is of 3 bytes. Then the last instruction is halt. As we know, this instruction is necessary so that subsequently, I mean in the consecutive memory locations in this part, some garbage is there. We have not stored anything. so that this part is not unnecessarily interpreted as instruction. This is necessary. Now, from this we can see that the instructions as they fetched one after the other from the memory locations, they are interpreted by the microprocessor. Now, we can see 3A is the opcode. On the other hand, 3A is also part of the address. That means same thing may represent an opcode, same thing may represent some address or data. It all depends how inside the CPU it is interpreted. So that the interpretation is proper, it is necessary to follow some well defined format. So, it is necessary to use well defined format for these instructions. Otherwise, the microprocessor, the CPU will not be able to interpret these instructions as they are fetched into the CPU. Now, so we shall discuss in this lecture the format of these instructions, various instructions. Apart from that, let us try to understand what are the various issues that is involved in understanding instruction set. Another important aspect is the data types, or in other words, how data is represented and how it is processed inside the processor. So, here for example, in the memory location 003A, some data was stored. How it is stored in here, in what form, that has to be understood, and also how the addition is being performed, what kind of data types it is processing. For that purpose, you have to understand what are the different types of data types a microprocessor is processing or executing at a part can execute. Finally, you have to understand various addressing modes. What are the various addressing modes? What do you mean by that? What do we mean by addressing modes? We have seen that you have to represent or reference data, you have to reference address or instruction inside the memory, and you can do it in a number of ways, in several ways. What are the different ways one can do? One can represent, you can point to a memory location which stores data or instruction or address, and that is decided by the instruction addressing modes. So, we shall study these three aspects of the instruction, or these are the three ingredients which makes an instruction, and the instruction set is realized or implemented by comprising by proper mix of well defined format, different types of data types, and different types of addressing modes. So, first let us try to understand the data types or data and its representation. What are the different types of data a microprocessor can process? As you know, the uh, the data that is we are familiar with can be of non-numeric or numeric in nature. But before I discuss about non-numeric and numeric data, it is necessary to understand what do we really mean by data. Data, by data we mean something which conveys some meaning. For example, this bit sequence as such does not convey any meaning, but whenever we say that bit sequence is the opcode of 8085 microprocessor, whenever we say that, that means this bit sequence has some meaning. In other words, how this bit sequence is interpreted is depends on uh, whether it is an opcode or data. That is why we can say that by data we mean something or an entity which conveys some meaning. Now, it can be non-numeric or numeric in nature. In case of non-numeric, it can be a sequence of characters. Now, the characters can be represented by using some codes. Usually inside computer we use a popular code known as ASCII code. ASCII stands for American Standard Code for Information Interchange. And the ASCII characters are 7-bit in length. All the alphabets A to Z, lowercase, uppercase, all the numbers 0 to 9, the other characters printable and some non-printable characters are also represented by ASCII code, because you can all total represent 128 different types of characters by using ASCII code. Now, whenever you are storing some non-numeric data inside the processor, we use ASCII code. But usually you will find that most of the processing is done on numeric data. So, how the numbers are represented inside the processor, we have to understand. And first of all, before we consider the number representation, the way it is done by the processor, let us try to understand the number systems with which we are familiar with, that is your decimal number system. As you know, because we have 10 fingers, we use 10 symbols 0 to 9 to represent numbers, and it is called the decimal number system. Or and as you know, suppose you have to represent n digit number, it can be represented by an minus 1, an minus 2, a1 and a0. So, these are the n digits, and each of these digit ai can be from, it can be 0 to 9, it varies from 0 to 9. So, each of these digits can have values 0 to 9. Now, how the value of this number, n digit number, is calculated? N is equal to a n minus 1 into r to the power n minus 1 plus a n minus 2 r to the power n minus 2 plus dot 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 plus a1 r to the power 1 plus a0. Here the value of r is 10, which is known as the radix of the number system. So, in this particular case, the radix is 10. Now, how this value is calculated? Let me illustrate with the help of an example. Suppose the number is 1949. How we got it? 1949 is equal to 1 into 10 to the power 3, because it is a 4-digit number, plus 9 into 10 to the power 2 plus 4 into 10 to the power 1 plus 9. That is how we got it. And as you know, this decimal number system we commonly use in our day-to-day applications, because earlier all the computations were done with the help of by counting fingers. So decimal number is very popular in our day-to-day life, but this decimal number system cannot be used inside the processor. We cannot represent 1, 2, 3, 4, 9 because everything has to be in terms of zeros and ones, and that's why we use a binary number system inside the computer. And in binary number system, you can represent numbers in several ways. The simplest is known as sign magnitude. In which it has got two components, sign and magnitude. Suppose you are representing the value of 25. How it is done? It is represented in terms of zeros and ones in this manner. So we can extend the concept here. Here it will be just like your decimal numbers. We can extend it in this way. It will be here the radix will be 2. So it will be, say, for an n digit number, the value will be a n minus 1 r to the power n minus 1 plus, where r is equal to 2, plus a n minus 2 r to the power n minus 2. So in this way a0. For example, 25 is represented as 1 1 0 0 1. So in this particular case, your ai can be either 0 or 1, and r is equal to 2 as I have told, which is known as the radix of the binary number system. Now, how do you get 25? 25 is obtained by, say, 25 is equal to 1 into 2 to the power 5 to the power 4 plus 1 into 2 to the power 3 plus 0 into 2 to the power 2 plus 0 into 2 to the power 1 plus 1. That's how you got 25. Now, how do you represent sign? In case of decimal number system, we discussed earlier, we use two symbols. We use a symbol positive and negative to represent positive numbers, and negative to represent negative numbers. So we cannot store positive or negative symbols inside the processor, inside the memory of the computer. So we have to use something else. We can use the symbol, we can use, say, 0 to represent positive, 1 to represent negative. So plus 25 will be represented by 0 1 1 0 0 1, or minus 25 will be represented by 1 1 1 0 0 1. So this is the sign magnitude form of representation. Now, sign magnitude is not the only way of representing numbers in binary number system. Another alternative technique is known as ones complement form. In ones complement form, suppose it is 8-bit, it is an 8-bit number. So plus 25 in ones complement form is represented by 0 0 0 1 1 0 0 1. So altogether it is 8-bit. Here this is the sign bit, and these are the value of that or the magnitude of that integer number. How do you represent minus 25 in ones complement form? It is simply bit by bit complementation of each bit. We get 0 1 1 0 0 1 1 1. and this is the minus 25 in 1's complement form. And here we see that sign for positive is 0, sign for negative is 1. That is being retained, and we get this representation. And there is another representation, another alternative scheme that is used in binary number system is known as 2's complement number system. In 2's complement number system, say the positive number, say plus 25, is represented in the same way, say 0, 0, 0, 1, 1, 0, 0, 1. However, minus 25 is obtained by bit complementation and then adding 1 to it. So we get 1, 1, 1, 0, 0, 1, 1, 1. That's how you can get the 2's complement representation of minus 25. And this 2's complement form of representation is very popular inside the microprocessor and microcontrollers. The reason for that is it has got some advantages. What are the different advantages 2's complement number system provides? First of all, it has only 1 0. In case of 1's complement number system, it has got 2 zeros. For example, positive 0 is all 0 and negative 0 is all 1. So it has got two zeros, and sign magnitude form also has got 2 zeros. This part will be 0 and 1, and this part will be 0. So you get one less number. On the other hand, in case of 2's complement number system, it has got one unique 0. For example, for 8-bit 0 is 0 0 0 0 0 0 0 0. Now suppose you do the complementation, bit by bit complementation, and then if you add 1, you again get 0 0 0 0 0 0 0 0. So the positive and negative zeros has the same representation. That's why it has got only 1 0 representation in 2's complement number system. Not only that, it has got another advantage. The advantage comes from the hardware realization. You can perform addition and subtraction by the same hardware. And primarily because of this reason, that addition and subtraction can be realized by using the same hardware, 2's complement system is widely used in almost all microprocessors, and almost it is de facto standard for representing numbers inside the microprocessors and computers. Now, apart from this binary number system, sometimes you have to represent other numbers, for example, decimal numbers, inside the microprocessor. How you can do? The decimal numbers can be stored inside the memory. For example, in 1 byte, you can store it in this manner. You can store as, say, this part represents the BCD number, binary number, a decimal number 1010. That is your 10. Actually, it will be from 0 to 9. So I think it will be, say, all 0 to, say, 0 0 0 1. 1, for example, is stored and the other part, the remaining 4 bit, is not used. You can store a BCD number in binary coded decimal form you are coding in binary using 4 bits, and the remaining part is not used. This is known as unpacked representation. You can also store in packed form by storing 2 BCD values inside a single byte. For example, you can store in these 4 bits, if you want to store 4 0 1 0 0, and you can store 3 0 0 1 1 in 1 byte, and this is known as packed form of BCD representation. So you can store packed as well as unpacked BCD numbers in these two ways, and you will find that the numbers usually for 8-bit microprocessors, it will be 8-bit word, where the least significant bits are stored in bit 0, and most significant bit is the sign bit, and 7 bits are stored here. If the processor is 16-bit, then the least significant bit will be the D0 will be the least significant bit, 0th bit, and most significant bit will be that 15 bit will be the sign bit. This is how it is represented inside the microprocessor, and it is known as the little endian convention. Now, let us focus on the instruction format. So, we have discussed the typical the way the numbers are represented, the 2's complement number. Now, let us focus on the instruction format, the way the different components of an instructions are stored inside the processor. As we shall see, an instruction will have different components or different parts, and how these different parts are organized in an instruction is known as the instruction format. Now, an instruction format has to pass on some information to the CPU. For example, an instruction format must have opcode. So, one particular component of an instruction has to be opcode. What are the other components necessary, which has to be conveyed to the CPU to execute an instruction? First of all, it must have source address of operand 1. Suppose you are performing addition of two numbers. You have to provide the source address of operand 1, source address of operand 2. You have to provide where the result will be stored, and finally, where from the next instruction will be taken for execution. So, the different components will be source address of operand 2, and the destination address of result, where the result will be stored, and finally, you have to provide the address of the next instruction. Now, if you want to provide all this information, opcode, source address of operand, source address operand 2, destination address, and address of next instruction, I mean particularly these addresses in an explicit manner, the instruction size will be quite big. Let's assume the opcode size is 1 byte. Source address, as you have seen, for 8-bit microprocessors, the address size is of 2 bytes. So you will require 2 byte to explicitly specify the source address of operand 1, then 2 byte to specify the source address of operand 2. Destination address also will require 2 bytes. Address for next instruction will also require 2 bytes. So altogether it comes to 9 bytes. So you will require 9 bytes to store just one instruction. Obviously, it will occupy a very large memory whenever you are storing a big program comprising several instructions. Then it will require a large memory to store a program, and it will also take long time to execute, because you have to fetch a single instruction from 9 memory locations. So the time required to fetch the instruction, a single instruction, will be quite long. So you have to devise some technique by which this can be avoided. So the basic objective of realistic instruction format is shorter size, that means each instruction does not require a large number of bits to represent a number, and also it should take shorter time to execute. These are the two basic objectives of suitable instruction format. How it can be achieved? For that purpose, several techniques are followed. Number one is to use a special register known as program counter. How program counter helps? Suppose this address is removed from this, and we always say that there is a register inside the CPU known as program counter, which always holds the address of the next instruction. So if you can organize the instructions in consecutive memory locations, as we have done in this particular case, as you can see here, the instructions are stored in consecutive memory locations. So if you can store that simply by implementing the program counter from this location, and after this instruction is executed, it will point to this location, then the program counter will point to this location, and in this way the program counter will be implemented with the help of the timing and control unit to point to the address of the next instruction. Then we can get rid of this field of the instruction. So this address of the next instruction need not be explicitly specified as part of the instruction if program counter always holds the address of the next instruction. However, this cannot be always done. Later on we shall see there are some instructions where the next instruction to be executed is not the consecutive memory location. For example, you have to jump to another location. There is a subroutine call, or some interrupt occurs. You have to jump to some interrupt service subroutine. In such cases, you have to explicitly provide the address of the next instruction. But in most of the cases, the program counter will provide the next instruction, and this part is not necessary. Another technique to reduce the size of the instruction is to use accumulator. Accumulator to hold one of the operands always. That means the accumulator always provides one of the two operands or one operand if it is necessary in an instruction. Since the source of one operand is the accumulator, this particular field need not be provided as part of the instruction. Then another approach is to use source and destination address same. So, use same source and destination address. So, in such a case, for example, the source of operand 1 was accumulator. You can store the result, that means the destination, in the accumulator itself. So, accumulator is the source of address as well as it is the destination of the address. You will store the result in the accumulator. So, this part of the this part need not be, destination address need not be provided as part of the instruction. So, we have been able to remove the source of operand 1, destination address and address of the next instruction from the instruction. Another approach is to use the general purpose registers. Use of general purpose registers. We have seen the microprocessor is provided with a number of general purpose registers. In 8085 there are 6 general purpose registers. Instead of specifying the operand in memory location, you can specify the operand in a register. So, in such a case it can be very well accommodated as part of the instruction. There will be no need to have separate address. So, this is how you can reduce the size of the instruction, and you will see whenever you use the general purpose registers as the source of operand 2, then the time required to fetch the operand from the memory will be reduced. So, it will take shorter time to execute. So, use of these techniques, use of program counter, use of accumulator, use of same source and destination address and use of general purpose register leads to shorter instruction size and shorter time for to execute. Based on this, you can devise the instruction formats. Let us see what is the instruction format used in 8085 microprocessor. In 8085 microprocessor, the instruction format can be broadly divided, rather the instruction formats has got 3 types. There are 3 different formats. It can be classified by using number of bytes, the number of bytes that is used to represent an instruction. One way of classifying instruction is the number of bytes it requires. It can be, an instruction can occupy only 1 byte. So, it is called a single byte. So, in this case the single byte will essentially store the opcode. So, opcode is stored in this single byte where D0 and D7, these are the different fields, bits. Or the instruction can be of 2 bytes, where the byte 1 will be the opcode and second byte can be used to store the address. We can use either the data can be stored, or you can store address. So, the In this case it is 1 byte, in this case it is 2 bytes. There are some instructions where it will have 3 bytes. So in 3 byte instruction, the first byte will be the opcode, the second byte and third byte will hold the data or address. So these are the 3 different formats: single byte, 2 byte and 3 byte, which is used in 8085 microprocessor. Now, apart from specifying formats in terms of number of bytes, there is another way of doing it by number of operands, number of operand address. Number of operand address it specifies. For example, an instruction can be zero address. There is no need to explicitly specify any address in this particular format. So it is only the opcode. How do you specify the operands? The operand addresses are specified implicitly. As you have seen, accumulator is always the source of one of the operands. So in this particular case, if the instruction is monadic in nature, monadic means it involves only one operand. For example, you have to complement a number, or you have to perform say shifting of a number. So in such case, it will involve only one operand, and that operand is stored in the accumulator. So in this case, it is called zero address instruction. There is no need to explicitly specify the address. However, it may be necessary to specify one address. It can be one address. Whenever you are specifying one address, the first byte is opcode, second byte can be some address, for example IO address. As we shall see later on, the address of a memory location, IO location, can be specified by 8 bit, because the number of IO addresses is 256. So by using 8 bit address can be provided as part of this, and of course whenever you specify an IO address, the other operand address is implicitly specified by this opcode. That means the other operand, either the source or destination, is the accumulator. Now, even in it can be, sometimes you have to specify 2 address also. So a 2 address instruction can be of single byte, 2 byte or 3 byte. For example, whenever you are specifying 2 address, one address can be specified in register. So here it can be SSS, where SS is the source address of one of the operands specified in a register, and another address is specified by these 2 bytes. So in 8085 we will find that the lower order byte is stored first. This is the lower order byte of address, and this is the higher order byte. So higher order byte is stored here, and this is, for example, whenever, as we have discussed in this case, this particular example, here is the
address 003A. 00 is the higher order byte, 3A is the lower order byte. As you can see here, the 3A is stored first, byte 2, and 00 is stored in byte 3. This is the convention of their little endian convention, as I said. Little endian convention. In this, lower order byte is specified first, then followed by higher order byte. So these are the different formats that is being used in 8085. You see, we have already specified that your instruction can be of 1 byte, 2 byte, or 3 byte. What is the correspondence between the number of operands specified, 0 address, 1 address, 2 address, and the number of bytes that can be used? It is possible to specify 2 address in a single byte. For example, say 2 address can be specified even in a single byte. If you use the register, for example, the source, one of the source address, one register can be specified by 3 bits, destination register can be specified by another 3 bit, and these 2 bits forms the opcode. So with the help of a single byte, it can be of 2 address. So this 0 address, 1 address, and 2 address has no direct correspondence with single byte, 2 byte, or 3 byte. A 2 address can be a single byte instruction, can be a 2 byte instruction, or can be a 3 byte instruction. So to summarize, in this lecture, we have introduced to you the different types of data or data types that is used in microprocessor, that is TwosComplement number that is being used, and also we have introduced the instruction formats, and we have discussed the basis of the instruction formats, how the instruction format is so important, and the instruction format that is used in 8-bit in 8085 microprocessor. In the next lecture, we shall discuss the another important aspect of this instruction set, that is your addressing modes of microprocessors. Thank you.